In the quiet halls of modern physics, a new kind of matter has emerged, something so strange, so precise, that even the laws of the universe had to pause for a moment. It is called a time crystal, a form of matter that does not just exist in space. It exists in motion forever. Unlike ordinary crystals, salt, diamonds, or snowflakes, which repeat their structure in space, a time crystal repeats itself in time. It pulses, it oscillates, and incredibly, it does so without using any energy. That single fact breaks one of the most sacred rules of nature, the law of thermodynamics. Nothing in theory should move forever without losing energy. Nothing should tick endlessly without an external force, and yet time crystals do. In this documentary, the Wonder Lab explores how a once impossible concept leapt from theory into the laboratories of quantum physicists. We'll uncover how Nobel laureate Frank Wilczek first imagined time crystals over a decade ago, and how, years later, quantum computers at Google and Harvard turned that idea into reality. This is not science fiction. This is a new state of matter, one that dances with time itself. It challenges everything we know about motion, energy, and the arrow of time. Welcome to the Wonder Lab, and welcome to the strange, elegant world of time crystals, the matter that should not exist. For centuries, humanity has tried to categorize everything the universe could build. Solids, liquids, gases, and plasmas, the four fundamental states of matter taught in every classroom. But science has never been content with limits. In the 20th century, physicists began to push deeper, revealing hidden layers of nature: Bose-Einstein condensates, superfluids, quantum spin liquids, exotic states where the familiar rules of physics bend and twist. Each new discovery revealed not only what matter is, but also what it could be. And then came a question that shattered even the foundation of that understanding. If matter can organize itself in space, can it also organize itself in time? This question was not born out of fantasy, but out of deep theoretical reasoning. In 2012, Nobel Prize-winning physicist Frank Wilczek proposed something radical: a crystal, not in three-dimensional space, but in the fourth dimension, time. Wilczek imagined a structure that would repeat its pattern, not by spatial symmetry, but by temporal symmetry. Just as the atoms in a diamond repeat in regular intervals in space, he theorized that a time crystal's atoms could repeat in regular intervals in time without consuming energy or degrading. It sounded absurd. Perpetual motion? That violated the second law of thermodynamics, the foundation of all physics. Energy cannot simply circulate forever without loss, or so we believed. But Wilczek wasn't proposing a machine. He was proposing a state of matter, something governed by the deep laws of quantum mechanics, not by the classical rules we use to describe the macroscopic world. At first, the scientific community resisted. The idea of a time crystal was dismissed as poetic, beautiful, but impossible. Many physicists argued that such a system could never remain stable, that the randomness of thermal energy would destroy any repeating motion. And yet, in the realm of quantum systems, where particles can exist in superposition in multiple states at once, and where energy landscapes behave unlike anything we experience in the visible world, the impossible begins to look possible. The seed of the idea was planted. Could there exist a system that defies equilibrium? A material that never truly rests, not because of energy input, but because of the quantum laws that define its ground state. This became one of the most intriguing quests of modern physics, to discover if nature could indeed host a fifth state of matter, one that exists beyond time's flow. Over the next decade, That theoretical idea would evolve into one of the most extraordinary laboratory achievements of the 21st century. A real, measurable, observable time crystal shimmering within the circuits of a quantum computer. But before that breakthrough, scientists had to solve a riddle that cut to the heart of quantum mechanics itself. How do you make something move forever without energy? In the world we experience, motion and energy are inseparable. A pendulum swings because energy is transferred from potential to kinetic. A planet orbits a star because of gravitational pull and momentum. Even the tiniest atom vibrates because of energy within its bonds. But motion without energy? That's not just unnatural. It's forbidden by the very laws that define reality. This impossibility is governed by the second law of thermodynamics, the pillar of all physical understanding. It states that in a closed system, entropy, the measure of disorder, always increases. Everything, from galaxies to human bodies, tends toward equilibrium. Movement fades. Heat disperses. Eventually, all systems reach stillness, what physicists call thermal death. So when Frank Wilczek suggested the idea of a structure that would move forever without consuming or losing energy, it sounded like heresy. It resembled the mythical perpetual motion machine, the dream that had haunted inventors for centuries. But Wilczek's vision was not about engineering a device. It was about quantum order, about how particles behave when stripped of classical intuition. In the quantum world, rules change. Systems are not bound by our macroscopic understanding of motion. Instead, they are described by wave functions, mathematical expressions that encode every possible state a particle can be in. Simultaneously, here, energy landscapes can have valleys, regions where a system can settle without losing stability. Normally, once a system finds its lowest energy configuration, called its ground state, it stays there. Nothing moves because there's nowhere lower to go. But what if the ground state itself was moving? What if, at the deepest possible level of energy, the system naturally oscillated, not because of heat or force, but because of the way its quantum states were entangled in time? This was the paradox Wilczek introduced, a state of matter that never stops evolving, even at absolute zero, where all conventional motion should cease. To understand this, physicists began to explore something known as spontaneous symmetry breaking. In normal crystals, spatial symmetry is broken. The atoms arrange themselves in repeating patterns, choosing specific positions rather than staying evenly spread. A time crystal, by contrast, would break temporal symmetry, choosing specific moments to repeat itself in time, creating a pattern in motion. Imagine a clock that ticks endlessly, but not because of gears or batteries. Instead, its very existence depends on the quantum relationships between its parts. Each tick is not driven by energy, but by the structure of time itself. In 2014 and 2015, theoretical physicists began to refine Wilczek's concept, realizing that a true time crystal could not exist in equilibrium. It would require a periodically driven system, something pushed in rhythm but which responds in a way that's different from the drive. This led to the concept of a Floquet time crystal, a system that, when periodically driven, begins to oscillate at a rhythm that's a multiple or fraction of the driving frequency. In other words, you tap it once every second, and it beats every 2. This discovery was profound because it revealed something hidden in nature. Quantum systems could exhibit time symmetry breaking, a natural rhythm that refuses to synchronize with its environment. The paradox was no longer theoretical. It had become a question of experiment. Could such a system be built? Could scientists watch matter evolve in time forever, without energy loss, without heat, without decay? To answer that, researchers turned to the only machines capable of simulating the fundamental behavior of reality itself: quantum computers. To take the idea of a time crystal from theory to reality, scientists had to do something extraordinary. They had to create a system where motion exists without energy, a structure that vibrates in time even at its lowest possible energy state. This wasn't just a matter of curiosity. It was a challenge to the very machinery of the universe. Creating such a system required a platform where quantum behavior dominates, where every particle can be precisely controlled, measured, and isolated from the noise of the external world. And that platform was the emerging frontier of quantum computing. In a quantum computer, information is stored not as bits, zeros and ones, but as qubits, quantum particles that can exist in a superposition of states. They can be 0 and 1 at the same time, oscillating between possibilities. And they can be entangled, their fates linked in ways that defy distance and time itself. This unique environment makes a quantum computer more than a machine for calculation. It becomes a laboratory for new states of matter. In 2021, a team of scientists from Google's Quantum AI Lab, working alongside researchers from Stanford, Princeton, and Harvard, set out to do something that once lived only in the imagination of Frank Wilczek. They would build a time crystal inside a quantum computer. Their machine was Sycamore, the same processor Google had used 2 years earlier to claim quantum supremacy. Inside it, 20 superconducting qubits were arranged and manipulated with laser-like precision. The scientists applied a periodic sequence of microwave pulses, a rhythmic drive meant to push the qubits in a repeating cycle, like a metronome. But the true test was this: could the qubits respond in a rhythm different from the rhythm they were driven with? Could they establish their own independent, stable pattern in time, a pattern that persisted indefinitely, immune to noise and heat? The answer stunned the world. The qubits began to oscillate, not in sync with the external drive, but in perfect subharmonic resonance, their motion repeated every 2 cycles of the pulse. This phenomenon, called discrete time translation symmetry breaking, was exactly what a time crystal should do. It was as if the qubits had found their own rhythm, one that existed within time, but not bound by it. What made it extraordinary was not the motion itself, but the fact that it didn't cost energy. No heat, no decay, no entropy increase. The system wasn't being powered. It was simply existing in perpetual motion as part of its fundamental state. The team monitored the qubits for tens of thousands of cycles. Each time the same behavior persisted. No drift, no slowdown. The system oscillated endlessly, a structure that, once set in motion, refused to stop. It was, as one physicist described it, a crystal that ticks but never ages. The experiment was verified and repeated in parallel by a separate group at Harvard and the University of Maryland, using trapped ytterbium ions instead of superconducting qubits. Their results matched. 2 independent systems, 2 completely different methods, and both showed the same behavior. Time crystals were not imagination anymore. They were real, and suddenly physics had a new problem. How do you define something that breaks time itself, yet obeys quantum mechanics perfectly? As one researcher wrote, "We didn't break the laws of physics. We found a corner of the universe where they bend." This moment marked a new dawn. Matter, it seemed, could now exist in dimensions that Einstein, Schrödinger, and even Newton had never envisioned. The discovery of the time crystal wasn't just a scientific triumph. It was a philosophical shock, because if motion could exist without energy, if rhythm could exist without decay, then perhaps time itself wasn't as fundamental as we once believed. To understand why time crystals stunned physicists, we must step deep into the foundations of reality, into the laws that govern all motion, all energy, and all change. For centuries, science has stood on one unshakable pillar, the second law of thermodynamics. It states that in any closed system, entropy, or disorder, always increases over time. Nothing can remain perfectly ordered forever. Heat spreads, energy dissipates, motion fades. Everything from stars to human life eventually slides toward equilibrium, toward stillness. But time crystals don't. They should decay. They should lose energy. Yet they don't. Instead, they display motion without energy consumption and order without entropy increase. To understand how, we have to reimagine what motion means in the quantum world. In classical mechanics, the physics of cars, planets, and pendulums, motion always requires energy. A pendulum swings because you gave it a push. Friction and air resistance slow it down until it stops. In contrast, in the quantum domain, particles can exist in superpositions, but in multiple states at once. And transitions between those states don't always consume energy. Time crystals exploit this quantum paradox. They both exist in a state called flocé many-body, localization, a condition where quantum particles, though being periodically driven, avoid thermalization. In simpler terms, when energy is pumped into the system in a repeating pattern, instead of absorbing it and heating up, the particles lock into a rhythm. They don't get excited or lose coherence. They simply synchronize into a pattern that repeats in time. Imagine a row of dancers who are given a beat to follow. Instead of dancing to the beat, they choose to move every second beat, perfectly synchronized with each other, yet independent from the rhythm that drives them. No energy is spent on sustaining their motion. It's simply built into the quantum choreography of the system. That is what a time crystal does. It breaks time translation symmetry. Time translation symmetry is one of nature's deepest laws. It says that the laws of physics are the same today as they were yesterday and will be tomorrow. A falling apple behaves the same way now as it did 1 billion years ago. But a time crystal doesn't play by that rule. Its internal structure changes and oscillates as time passes, even though the external forces acting on it remain constant. In other words, it doesn't just exist in time, it creates its own temporal pattern. This breaking of temporal symmetry is the time domain equivalent of how normal crystals break spatial symmetry. In a regular crystal, atoms arrange themselves in repeating patterns in space, creating shapes like cubes or hexagons. In a time crystal, that repetition happens in time. It's a lattice not of atoms, but of moments, and here lies the most fascinating part. The motion is not perpetual energy, it's perpetual order. No energy is being extracted or generated. The system is in its lowest energy state, its ground state. It just happens to move within that ground state. To an outside observer, it looks like perpetual motion. But to the laws of physics, it's simply a new kind of equilibrium, one that oscillates instead of rests. Frank Wilczek, the Nobel laureate who first proposed the idea, once said, "If you can have a crystal that repeats in space, why can't you have one that repeats in time?" It sounded poetic, even whimsical, until quantum mechanics made it real. This discovery forced physicists to re-examine what stillness truly means. Perhaps there is no such thing as absolute rest in the quantum universe. Perhaps everything, from particles to galaxies, exists in some form of rhythm, invisible to us. Time crystals show that motion can be fundamental. They suggest that change, not stasis, might be the most basic state of matter, and if that's true, then the arrow of time, the one-way flow from past to future, might not be as unbreakable as we thought. In the timeless dance of the quantum world, time itself may not be a river. It may be a pattern. Time has always been the most mysterious dimension of all. We can see space. We can move through it. But time is something we feel, not something we can ever truly observe. For centuries, physicists believed that time was a smooth, unbroken flow, a universal clock ticking forward for everyone, everywhere. But when Einstein came along, that illusion shattered. He showed that time bends, stretches, and slows depending on gravity and motion. There is no single now. Every observer carries their own version of time, shaped by the geometry of space itself. And then came quantum mechanics, which added a new twist. At the tiniest scales, time doesn't flow continuously. It behaves in discrete jumps like frames in a movie reel. Particles can tunnel through time, skip intervals, and even exist in superpositions of temporal states, being in two different moments at once. For decades, physicists struggled to reconcile these two views, Einstein's smooth geometric time and quantum theory's fragmented, probabilistic one. The two didn't fit together. But then came the discovery of time crystals, and suddenly a bridge appeared between these conflicting worlds. Because time crystals show that time itself can organize into structure, it can crystallize, it can repeat, it can have symmetry, and that symmetry can be broken. This was revolutionary because it suggested that time is not just a background dimension through which things move. Time might be a material property, something that can take shape, respond to forces, and even change its texture under the right conditions. When the Google and Harvard teams observed qubits oscillating without decay, what they saw wasn't just quantum behavior. They saw time becoming granular, locked into a rhythm. It was as if the flow of time had stopped being continuous and had become structured, divided into repeating intervals, each one echoing the last. Physicist Chetan Nayak described it beautifully. A time crystal is a system that remembers what time it is, even when isolated from the rest of the universe. This means that within its isolated quantum world, the crystal experiences a form of internal clockwork, a self-sustaining rhythm that doesn't depend on any external tick. It's timekeeping without a clock. It's order born from isolation. But the implications go far deeper than physics, because if a material can exist in multiple temporal states, if it can loop within time instead of simply flowing through it, then our entire notion of past, present, and future becomes uncertain. In classical thinking, the past causes the present, and the present shapes the future. But in a time crystal, these distinctions blur. The system doesn't progress through time. It repeats through it. Each cycle is both a memory and a moment. There is no clear direction, only recurrence. This resonates eerily with certain interpretations of quantum mechanics, such as the many worlds hypothesis, where every quantum event splits the universe into countless timelines. In a way, a time crystal can be seen as a microcosm of that, a miniature universe endlessly replaying its own rhythm, looping between possibilities that never fade. Some theorists even speculate that the entire universe might operate like a massive time crystal, a cosmic structure where the arrow of time emerges from quantum oscillations at the deepest level. In such a view, what we perceive as the flow of time is simply the macroscopic echo of these quantum rhythms, scaled up to cosmic proportions. It's an idea that blurs the line between physics and philosophy, because if the universe itself is oscillating, if time is not flowing but vibrating, then Maybe there was never a beginning, and there will never be an end. Only cycles, only patterns, only the endless dance of order repeating through eternity. And yet, as mind-bending as it sounds, every step of it can be tested, not through imagination, but through experiments, through qubits, lasers, superconducting circuits, and trapped ions, instruments that let us touch the very texture of time. What once belonged to science fiction is now a subject of peer-reviewed research. What once sounded impossible is now real. And as the strange glow of a time crystal pulses inside a quantum machine, it whispers something profound about our existence. That time might not be something we move through. It might be something that moves within us. For most of human history, new states of matter, from solids and liquids to superconductors and Bose-Einstein condensates, have reshaped technology and redefined civilization. Time crystals may become the next great leap in that story. Though they exist only in carefully controlled laboratories for now, their potential reaches into realms once thought impossible: computing beyond limits, clocks beyond precision, and energy systems beyond decay. But before we imagine the future, let's understand why time crystals are so unique. Unlike ordinary materials, which obey the gradual march toward entropy, time crystals exhibit non-equilibrium stability, meaning they can maintain structure and coherence indefinitely. They don't settle into disorder. They resist the natural tendency to heat up or lose information. This makes them a dream material for quantum technologies, systems that must remain coherent, isolated, and stable even under extreme conditions. Quantum computing. The next revolution, one of the biggest challenges in quantum computing, is decoherence. The tendency of qubits to lose their delicate quantum states through noise, heat, or environmental interference. Even a fraction of a second of instability can collapse a quantum computation. Time crystals, however, exhibit a strange form of temporal rigidity. Their internal oscillations are locked in perfect periodicity, unaffected by small fluctuations in their surroundings. That means a qubit encoded within a time crystal could, in theory, maintain its state far longer than any conventional qubit. Researchers believe this could lead to self-correcting quantum memory, a material that naturally resists the noise that destroys quantum information. Instead of constantly recalibrating the system, as today's quantum computers must, a time crystal-based processor could stabilize itself. Imagine a quantum chip that doesn't just compute faster, it computes with temporal harmony, using the rhythm of the universe as its clock. This is not science fiction. Teams at Google, Delft University, and the University of Tokyo are already exploring prototypes of time crystal-based qubits, attempting to integrate these oscillating states into quantum circuits. If successful, time. Crystals could become the cornerstone of a quantum internet, a network that uses entangled particles to transmit information instantaneously across vast distances, secured by the laws of physics themselves. Unbreakable clocks and energy systems. Another astonishing implication lies in timekeeping. Today's most precise devices, atomic clocks, measure time by counting the oscillations of atoms like cesium or rubidium. They are extraordinarily accurate, losing only about 1 second every 100 million years. But a time crystal clock wouldn't just measure time, it would manifest it, because the oscillation is intrinsic, self-sustaining, and requires no external drive. It could become a perfect temporal reference, immune to environmental noise. A clock based on time crystals could be the most stable object ever made by humanity, a rhythm that might never drift even after billions of years. Such precision could revolutionize GPS, satellite communication, astrophysical measurement, and deep space navigation. In a future spacecraft, time crystals might serve as quantum beacons, providing perfect synchronization between distant vessels traveling across interstellar space. Even energy systems could be transformed. While time crystals don't generate energy in the classical sense, their non-dissipative behavior could inspire materials and circuits that operate near zero energy loss, leading to ultra-efficient superconducting devices, perpetual oscillators, and logic gates that never overheat. It's a vision of technology not powered against nature, but in harmony with it, guided by the rhythms that already exist at the quantum level. Toward a new understanding of matter, but perhaps the most profound impact of time crystals won't be in machines. It will be in the way we understand reality. Because time crystals prove that matter can organize in the time dimension just as easily as in space. They show us that the structure of reality is not static, it's rhythmic, dynamic, self-referential. In a sense, every physical system might be viewed as part of a vast temporal network, a cosmic metronome where galaxies, atoms, and time crystals all vibrate in harmony with different frequencies. The discovery of time crystals is a reminder that the laws of nature are not limits, they are invitations. Invitations to look deeper, to ask why, to find order where chaos once seemed absolute, just as superconductivity reshaped our understanding of electrons and quantum mechanics reshaped our understanding of atoms. Time crystals are reshaping our understanding of time itself. We are still at the dawn of this exploration, but what's clear already is that this strange new state of matter is not a curiosity. It's a doorway, one that leads to the deepest truths of existence. In the laboratories of today, where qubits hum in isolation and light pulses across superconducting chips, we are watching something extraordinary unfold, the first human attempts to engineer the flow of time itself. And in that quiet hum, we hear a whisper, not of machines, not of energy, but of the very rhythm of the universe, a rhythm that may have been there since the beginning. There are moments in science when a discovery doesn't just expand our knowledge, it redefines our place in the universe. Time crystals are one such moment, because hidden within their microscopic quantum dance lies a question that reaches beyond physics into the very fabric of existence. What is time? Since the dawn of civilization, humans have experienced time as an unstoppable current, a river that carries everything from birth to death, from creation to decay. We measure it with clocks, calendars, and lifetimes. We divide it into seconds, hours, and years. But the discovery of time crystals whispers something different, something ancient and radical. What if time doesn't flow at all? What if it beats? Just as matter can crystallize into patterns of atoms, what if time itself crystallizes into patterns of moments, repeating, pulsing, and enduring forever? When we look at the universe through this lens, everything begins to shift. The stars above us, burning for billions of years, may themselves be part of a grand cosmic rhythm, their fusion cycles resonating with invisible patterns across space-time. Galaxies, spinning in vast spirals, could be seen as echoes of this hidden temporal order, their motions not random, but harmonic. And if that's true, then perhaps the entire cosmos is a kind of universal time crystal, a structure where repetition, oscillation, and resonance are fundamental. The universe as a time crystal physicists have long believed that our universe is governed by symmetries, elegant mathematical patterns that give rise to forces, particles, and laws. Every known interaction, gravity, electromagnetism, quantum spin, emerges from some deeper symmetry. Now, with the discovery of time crystals, a new form of symmetry has entered the picture, time translation symmetry, breaking, and this may not be limited to small systems. If time symmetry can be broken inside a few qubits, could it also be broken at the cosmic scale? Some theorists, like Sean Carroll and Lee Smolin, have begun exploring whether the universe's evolution itself might follow oscillatory cycles, an infinite heartbeat of expansion and contraction, birth and renewal. A universe that dies and is reborn, not linearly but rhythmically. In such a model, the Big Bang would not be the beginning of time, merely one pulse in an eternal sequence of cosmic rhythms. Energy would not vanish, it would recur. Entropy would rise and fall like a breath, and perhaps, at the deepest level, the quantum oscillations that define a time crystal are a microcosm of that cosmic pulse, the same fundamental beat that animates everything from atoms to galaxies. The more we study these crystals, the more they seem to whisper of an order beneath time, a hidden metronome driving all existence. The end of permanence. To understand the scale of what this means, imagine this: every second of your life, every heartbeat, every thought, is part of the same rhythm that governs quantum matter. You are not drifting through time, you are vibrating with it. If time can be structured, it means permanence and change are no longer opposites. They are two faces of the same rhythm. In a time crystal, motion and stillness coexist. The system moves, yet remains unchanged. It's the paradox of the universe itself, creation and stability intertwined. For philosophers and cosmologists, this challenges the idea of time's arrow, the notion that time always points forward, from order to chaos, from birth to death. Perhaps deep down, that arrow loops back on itself. Perhaps the universe isn't moving toward an ending, but toward repetition. As physicist Marina Cortez once said, maybe the universe doesn't have time. Maybe the universe is time. The human perspective beyond the equations. This discovery stirs something profoundly human, because for the first time, science suggests that the patterns of existence we see in galaxies, tides, and heartbeats may not be coincidences. They may be reflections of the same universal rhythm. It means that the beat of a human heart, the oscillation of a qubit, and the vibration of space-time itself might all be expressions of a single truth, that the universe is alive with repetition. We, too, are part of that pattern, atoms in the crystal of cosmic time. When viewed through this lens, the discovery of time crystals becomes more than a technical milestone. It becomes a mirror, showing us that reality is not a straight line, but a dance, not a march, but a pulse, and as we uncover more about these strange oscillating systems, we may one day realize that the ultimate rhythm of the universe, the rhythm of time, was never out there. It was within everything all along. In the hidden laboratories of our world, places lined with liquid helium tanks, superconducting circuits, and the silent hum of cryogenic machines, scientists are no longer content with observing time. They are learning how to engineer it. Welcome to the quantum frontier, where the most advanced experiments on Earth are beginning to manipulate time itself. What once seemed like fantasy, bending the flow of time, reversing it or locking it into repeating patterns, is now becoming a technical reality. And at the heart of this revolution lies the strange and beautiful phenomenon of time crystals. Controlling time at the quantum level to create a time crystal is one thing. To control one, that's the next step. At institutions like MIT, Google Quantum AI, Oxford, and Caltech, Physicists are experimenting with new methods to tune the internal rhythm of time crystals. By adjusting microwave drives, magnetic fields, and interaction strengths between qubits, they can change the frequency of temporal oscillation, effectively controlling how time moves within the crystal. In one recent experiment, a team managed to pause the oscillation, hold it still, and then resume it, as if freezing a moment and restarting it on command. To them, it wasn't magic. It was quantum interference precisely choreographed across a network of interacting qubits. Each qubit acts like a tiny clock, and when they synchronize, they form a collective rhythm, a unified beat that defines the crystal's temporal structure. When manipulated correctly, this rhythm can be sped up, slowed down, or even reversed. The implications of this are staggering. It means that scientists are not only creating new forms of matter, they are programming the flow of time within those materials. In the near future, time crystals could become the processors of the quantum age, where computation happens not across circuits in space, but across oscillations in time, quantum memory that defies decay. The reason physicists are obsessed with this control is because time crystals could solve one of quantum computing's oldest problems. Decoherence quantum systems are fragile. They lose information easily when disturbed by heat, vibration, or stray electromagnetic fields. Even a tiny fluctuation can destroy the delicate superpositions that give quantum computers their power. But time crystals offer something never seen before: a naturally stable, self-reinforcing oscillation that resists decay. When encoded properly, a time crystal can store quantum information within its periodic rhythm. That rhythm doesn't fade, doesn't drift, and doesn't heat up. It's as if the system remembers its own state, a perfect, perpetual echo. Imagine memory units that never degrade, quantum processors that never lose synchronization, or quantum sensors that remain calibrated for centuries without adjustment. Such systems could make our current technology, even the most advanced supercomputers, look primitive. Time Reversal Experiments 1. Of the most astonishing frontiers being explored right now is time reversal, not in science fiction, but in quantum labs. Using time crystal-like dynamics, researchers can make quantum systems evolve backward, effectively undoing changes, restoring previous states, and reversing entropy on a local scale. It's not true time travel, but it's close to temporal symmetry control, the ability to reverse the arrow of time for a system, even while the rest of the universe moves forward. In these experiments, a quantum state is deliberately scrambled, then subjected to a precisely tuned series of pulses that reconstruct its previous configuration. What emerges is astonishing. The system returns to a state it should have lost forever. This hints at a future where time manipulation becomes an engineering discipline used to correct errors, preserve information, and maintain systems that, theoretically, could operate forever. It's as though scientists have learned to play music with time itself, striking chords that resonate not just in space, but in the flow of reality, the future of controlled time. If this sounds like something out of a dream, remember 50 years ago, quantum mechanics itself seemed absurd. The idea that a particle could be in two places at once, or that an observer could change reality simply by measuring it, was once dismissed as madness. And yet, here we are, watching physicists tune the tempo of time inside superconducting chips. In the decades ahead, time control may become as fundamental to science as electromagnetism is today. It may lead to breakthroughs we can't yet imagine. Quantum simulators that model the evolution of the universe itself. Temporal encryption, where data exists only at specific moments in time. Time-based logic gates, computing not through electricity, but through oscillation sequences, and even biological time synchronization, linking living systems with quantum rhythms for health and longevity. We are entering an era where time is not a constant. It's a variable we can engineer, and in that realization lies both power and mystery. Because to manipulate time is not just to advance technology, it's to touch the essence of existence itself. As one physicist from Google's quantum AI team said, we are no longer just studying the universe. We are learning to rewrite its tempo. And in that laboratory hum, beneath the flicker of quantum pulses and magnetic fields, the boundary between science and the sublime begins to blur. Time, once thought to be the unbreakable backdrop of all things, is becoming a material we can shape, mold, and understand. This is not the end of physics. It is the beginning of a new kind of science, one where the fabric of time itself becomes our next frontier. There is a quiet revolution happening, one that could change not just science, but the very definition of existence. For thousands of years, humans have been slaves to time. We measured our days by the movement of the sun, our years by the turn of the earth, and our lives by the slow rhythm of decay. Every heartbeat, every breath was one step forward into an irreversible future. But now, for the first time in history, humanity is learning to look back. Not metaphorically, literally. We are standing at the edge of a world where time is no longer an observer's prison, but a field to be engineered, shaped, bent, and rearranged at will. A universe of clocks, everything in nature, is a clock. The oscillations of atoms, the vibrations of molecules, the rotation of planets, all are ticking in rhythm. But for centuries, humans believed time was a one-way arrow, always forward, never back. Einstein shattered that illusion when he showed that time can slow, stretch, or compress, depending on speed and gravity. And now, quantum physics is going one step further, suggesting that time might not flow at all. At the most fundamental level, what we perceive as time might simply be a pattern of changes, a relationship between states, a rhythm of existence repeating itself. Time crystals prove this in their own eerie way. They oscillate in time without energy loss, defying thermodynamics. They show that motion can exist without progress, that change doesn't require time to move forward. It's not just strange, it's poetic. The universe itself, it seems, could be built from timeless rhythms, the dawn of temporal engineering. Now, imagine a future where humans harness this principle, temporal engineering, where we no longer observe time, but design it, where our machines don't just exist in time, but actively control its flow. Think of spacecraft that warp their local time fields to travel interstellar distances. Hospitals where time is slowed inside operating rooms, allowing surgeons to perform miracles. Data centers that store information in temporal sequences, immune to hacking because they exist only at specific instants in time. It sounds like fantasy by Michael Brispatz. But so did electricity once, or gravity manipulation, or the idea of quantum entanglement, and yet here we are, manipulating the smallest particles in the universe, forcing them to oscillate in defiance of entropy. If we can master time on that level, even for a few atoms, what's to stop us from doing it on a larger scale? The death of irreversibility. Physics has always bowed to one law, the arrow of time. Entropy increases, systems decay. Everything falls apart. But time crystals whisper a different story. They show us systems that don't lose order, that remain stable, eternal, and repeating. If entropy is not universal, if order can persist infinitely in pockets of space-time, then perhaps the universe itself is not doomed to fade into heat death. Perhaps there are regions of the cosmos, or entire realities, where time loops back on itself, where energy cycles endlessly, where existence never fades. And if humans can replicate that here in our laboratories, then we've done something profound. We've broken the ancient curse of impermanence. We've touched eternity. When physics meets philosophy once, philosophers asked, does time exist without consciousness? Now physicists are asking the same question, not in poetry, but in equations. If time can be engineered, manipulated, paused, or reversed, then what is time, truly? Is it a property of the universe or a projection of the mind? If time is an illusion created by observation, then perhaps our experiments with time crystals aren't just physical, they are existential. We are probing the fabric of perception itself, testing whether the universe needs time at all to exist. Maybe reality isn't a story written in linear order. Maybe it's a symphony, one where every note, every event exists simultaneously, and consciousness simply plays them one by one. And if that's true, then the future isn't something we move toward. It's something that's already here, waiting to be accessed, like a song we haven't yet heard. The human paradox. There's a paradox in all this. As humans strive to master time, we are still deeply bound by it. Our lives are short. Our memories fade. Our moments slip away. But that's what drives our wonder and our science. The very awareness of time's fleeting nature is what pushes us to understand it, to conquer it, to reach beyond the ticking clock and grasp something timeless. That's the paradox of progress. We chase eternity precisely because we know we don't have it. And maybe that's what makes this journey so human, a glimpse of what's coming already. The world's greatest scientific minds at Google Quantum AI, Stanford, CERN, and NASA are experimenting with the edges of temporal control, small steps for now, manipulating oscillations in superconducting qubits, controlling phase transitions, achieving coherent quantum memory. But those small steps are how revolutions begin. In the decades ahead, our descendants may look back at these experiments, at the first shimmering patterns of time crystals, and say, that was the moment when humans first touched the architecture of time, and perhaps someday we will build machines that live beyond time, processors that compute in loops, sensors that feel the pulse of space-time, and civilizations that no longer age. When that happens, humanity will no longer just exist within the universe. We will exist alongside it, co-creators of its rhythm. In the soft hum of a quantum lab beneath the faint glow of superconducting circuits, the story of time is being rewritten, not by gods, not by myth, but by us, humans, curious, fragile, and endlessly reaching beyond the now. And when that story is finished, one truth will remain. We were not meant to be prisoners of time. We were meant to understand it. There comes a moment in every age, in every civilization, when humanity looks up at the cosmos and realizes something breathtaking, that the universe is not a machine of chaos, but a story of patterns. For millennia, we have searched for order in the stars, in atoms, in the fabric of space. And now, in the quiet hum of quantum laboratories, we found it, not in galaxies, not in black holes, but in the smallest rhythm of existence, the time crystal, a fragment of matter that doesn't just exist in time, but creates its own time. Imagine this, a particle caught in perpetual motion, not burning energy, not decaying, not changing state, simply pulsing in harmony with the invisible beat of the universe. No friction, no loss, just motion, forever. For the first time in history, we have witnessed matter that defies the arrow of time, that breaks one of the universe's most sacred laws, not through fantasy, not through magic, but through physics, and in doing so, we've taken a glimpse into something greater, something beyond the equations, beyond entropy, beyond everything we thought we understood. When time itself can crystallize, what else might be possible? Could consciousness be another rhythm, another pattern of existence? Could the mind, like matter, oscillate in endless cycles, forever reborn in the tapestry of space-time? These are not questions for scientists alone. They are questions for all of us, for anyone who has ever looked at the stars and wondered why we exist and how everything began, because the discovery of time crystals doesn't just change physics. It changes what it means to be alive in time. Our ancestors once looked at the rising sun and thought it was the heartbeat of a god. Today we look at a shimmering pattern of atoms and realize it is the heartbeat of reality itself. Maybe, just maybe, time has never been something we move through. Maybe it's something we are, a living pattern, eternal, repeating infinite. When the last star fades, when galaxies grow cold, when even black holes evaporate into silence, the rhythms of time crystals may still pulse in the void, whispering that not everything fades, that somewhere in the endless dark, order survives. And perhaps that's the truest miracle of all, that we, the children of time, have learned to shape the very thing that shaped us. So, as you listen to this story, remember, the future is not ahead of us. It's within us, waiting to unfold one discovery at a time, because every time we ask, what if? Every time we push the boundaries of what's possible, we are not defying time. We are defining it. This is not the end. It's the beginning of a new rhythm, a rhythm born in the quantum heart of creation. And that rhythm is the Wonder Lab.